We'll review on some joint work with André Bellotto and Octave Curmi, so about the semi-analytic locus of a subanalytic set. So I will start with sorry, I have a small problem here. It's not the right file, but I will do with this one, sorry. We'll start with by recalling the Tarsky-Seidenberg theorem. So I consider an algebraic subset of Rn plus P denoted by X, and I consider the pi, the projection on the first n components of of Rn plus 1. So the image, the theorem asserts the following: the image of X by this projection pi is a semi-algebraic subset of Rn. So here, the semi-algebraic subset is a finite union of sets defined as follow. So it's a set. There are sets defined as by the vanishing of polynomial and some polynomial inequalities. So here, P and the Qi's are polynomial functions. So in particular, this implies the following fact: is that if I consider P of X and its Zariski closure, so its Zariski closure is by definition the smallest algebraic set containing pi of X. And because pi of X is semi-algebraic, then the dimension of pi of X is also equal to the dimension of its Zariski closure. And we can also prove that it's less than the dimension of X itself. Okay, so this is true for any projection map, but in fact, it's true for any algebraic map. Because if you consider an algebraic map from Rp to Rn, then we can factor this map through its graph. And by applying the previous result to pi, we obtain the same for phi. Okay, so this is the situation in the algebraic case, and I'm interested in the analytic case. So now I will talk about the analytic case. So we can define in the same way as we define semi-algebraic sets, we can define semi-analytic sets. So we say that X in Rn is semi-analytic if locally at any point of the ambient space, X is defined as a semi-analytic, semi-algebraic set, but where we replace polynomial function by analytic function. So it's a finite union of subsets defined by the vanishing of some analytic function fi and some inequalities involving real analytic function, the GIL here. So this notion of this semi-analytic subset have been deeply studied by Wojciechowicz in the 60s. But it was known for a long time that there were no analog of the Tarsky-Seidenberg results in this situation. By an example due to Osgood, let's say the following. So we consider phi here. It's a map from R2 to R3, defined in the following way. So phi of uv is just u exponential v. So what I claim is that the Zariski closure of the image of R2 is exactly R3. So here by Zariski closure, I mean the smallest analytic set containing the image of R2. So why this is the case? It's just because if we consider f, let's say f of x1, x2, x3, let's say convergent power series, so it's zero locus defined an analytic subset in the neighborhood of the origin on R3. Imagine that f contains the image of phi, so it means that f of let's say uv and u exponential v is equal to 0. So we can expand f as a formal sum like this of fd, where d runs over the natural numbers, and fd is a homogeneous polynomial of degree d. So if I replace x1, x2, x3 by u, uv, u exponential v, I obtain that the sum of the fd of u, uv, u exponential v is equal to 0. And therefore, we obtain that the sum of u to the power d times fd of 1 v exponential v is 0. Therefore, the coefficient of ud is 0 for any d. So this is this term, which is equal to 0. And because 1 and v and exponential v are algebraically independent over q, then, or over r, then sorry, the FD are identically 0. So therefore, the initial power series F is identically equal to 0. So there is no other function than the 0 function that vanish on the image of R2. So this means that the Zariski closure is exactly R3. So in particular, this image cannot be semi-analytic. So that's a counterexample to an analog of Tarsky-Seidenberg result in this situation. So this was the justification to the introduction of what is called a subanalytic set. So we say that a set X in Rn is subanalytic if locally at any point of the ambient space, Rn, X is the proper image of a semi-analytic set. So this terminology has been introduced by Hirunaka, but this kind of set has been studied before by Gabriel, Art, and Tame, for instance. And the goal of my talk is to answer the following question. How far is a subanalytic set from being semi-analytic? So we'll start by giving the answer. We consider here a set X, subanalytic in Rn, and I denote by SA of X the set of subanalytic points of X. That is the set of of points in the ambient set Rn at which the germ of X is semi-analytic. And the answer is the following result due to Pawłowski that says that the complement of this set, so the set of points at which X is not semi-analytic, is itself a subanalytic set and of small dimension compared to the dimension of X. It's of dimension less than the dimension of X minus 2. So Pawłowski proved this result in a long paper at the beginning in 90, I think, yes, exactly 90. And we recently gave a new proof of this result. And the goal of my talk is to present the main ideas of our proof. Okay, so before entering into the details of the proof of this result, I will talk about some other notion that I need for explaining the proof. So first, I will introduce some ranks. So I consider a general map phi here, which is an analytic real map from Rp to Rn. And I denote by R of phi its generic rank. So the generic rank of the Jacobian matrix in the neighborhood of the origin. So that's my first rank. I can also consider phi star. So phi induce a morphism between the rings of convergent power series, R of xn, x1, xn, and R of u1, up. And I can define the second notion of rank, the analytic rank, or A, phi, which is the dimension of the ring of convergent power series modulo the kernel of this map, ring morphism. So in my previous example of the example of Osgood, I come back to the previous example here. We proved that, if F was in the kernel of the map of Osgood, then it was 0. So this means that it's here. This means that the kernel of phi star is exactly equal to 0. So the dimension that we obtain here is just 3 because it was defined from the ring of power series in 3 variables. So in the example of Osgood, this rank is exactly equal to 3. Okay, while the generic rank is equal to 2. So these two ranks are different. Okay, we can also define the analog of this rank in the formal case. So the map phi induces a ring morphism between the rings of formal power series, defined in the same way as phi star. So we denote this completion of phi star by phi hat star. And I can define in the same way the formal rank of this map. So here again, in the example of Osgood, there is no difference. If a formal power series vanishes along the image, it's 0. So this kernel here, it's identical, is 0. and therefore this dimension is also equal to 3. Okay. So in general, we have these inequalities. The generic rank is always less than the formal rank, which is less than the analytic rank. And not exactly in this way, but Grothendieck asked the question if these two ranks were equal. His initial question was not exactly like this one, but it was equivalent. And the answer has been given by Gabriel in 73 by the negative, considering the example of Osgood in the following way. So we consider phi star, the morphism induced by the map of Osgood, this one. So as I said before, phi star is injective, okay, because the only power series f such that this is equal to 0 is f equal to 0. So the kernel is equal to 0 for phi star is injective. This is the same for phi star hat. It's also injective. But Gabriel remarked that there exists a convergent power series G of U and V that is the image of a divergent power series. And it cannot be the image of a convergent power series because this map phi star hat is injective. Okay. So then he defined the new ring morphism psi from the ring of convergent power series in 4 variables, x1, x2, x3, x4, defined in the following way. So psi of f is just f of u, uv, u exponential v, and g of uv. So we can remark that the formal power series x4 minus s hat of x1, x2, x3 belongs to the kernel of phi, sorry, not phi, psi star hat, like this. Okay, because the image of x4 is G and the image of S hat is also G by construction. Okay, so this psi hat star is not injective, and in fact we can prove that this power series is a generator of the kernel of psi hat, like this. Okay, there is no star here, sorry. But we can prove that psi is injective because there is no way to find, because in fact, in some senses, G is not the image of something converged. I do not give the details to be technical, but we can prove that psi is injective. So psi is injective. This means that the analytic rank is exactly 4 because the kernel is equal to 0. So we need to consider the dimension of this ring modulo 0, so 4. Because the kernel of psi hat is principal, it's generated by 1 element, then the dimension drops and the formal rank is equal to 3, while the generic rank is also 2. Okay, so this example shows that the 3 ranks, the generic rank in here is less than the formal rank, which is less than the analytic rank. Okay, so these 3 ranks can be all different. Okay. And 2 years later, Gabriel gave, in fact, a positive result in the direction of studying these ranks, which is the following one. So this is called the Gabriel's rank theorem. It says that if the 2 first ranks are equal, then the last one is also equal to these 2 ranks. So if the generic rank is equal to the formal rank, then it's also equal to the analytic rank. Okay. So a map satisfying this result, so for which the 3 ranks are equal, is called regular in the rest of the talk. So you can think about this last inequality, formal rank equal to the analytic rank, as saying that the kernel of the completion of the morphism phi star is generated by the kernel of phi star. There is no new formal relation between the images of the coordinates by phi. Okay, so last year we gave a new proof of this result of Gabrielov, and we gave also equivalent statements. And this one is on one of them. So we can rephrase the result in different way, let's say the following one. So we consider a convergent power series F depending on variables x1, xn, and one particular variable denoted by y. And assume that we can multiply F by some formal power series G, which is not equal to 0, such that F times G becomes a polynomial in Y. Okay, it's a formal power series that it's polynomial in the variable Y. Then we can do the same in the convergent way. That means that there exists a convergent power series H, non-zero, such that F times H is also polynomial in Y. So these results, which is purely algebraic in the statement, raise the question of having a proof which is more algebraic, because the original proof of the proof we gave and the original proof of Gabriel Frank theorem is an intricate, let's say, we use different tools, analytic tools, topological tools, commutative algebraic tools also. And the question is to find a more algebraic way of proving this result, let's say like this. So the question is, can we extend this result to a more, let's say, general and algebraic setting? So the answer is yes. And we can give sorry, problem to change my, okay. So for this, I need to introduce what is called Weierstrass temperate families. So I come back here, sorry. I want to extend the previous result to a more algebraic setting. So what this means, it means that can we find the same kind of result where the ring of convergent power series are replaced by other types of rings? So the answer is yes, and the other type of rings we need to introduce are what we call Weierstrass temperate families. So I fixed a field K. So here K is, this K here is a characteristic zero field that I assume algebraically closed for simplicity and uncountable. And for any integer n, I denote by K of double bracket like this, K is subalgebra of this ring of formal power series. So we say that this family of algebras, one algebra for each natural number n, is called the Weierstrass temperate families if it satisfies several axioms. I will not enter in the details of all of them, but first we can say that they form a Weierstrass family. So this notion of Weierstrass family has been introduced in the 80s by Denef and Lipschitz in order to extend some Artin approximation results. In particular, this means that these rings satisfy the Weierstrass division theorem, which is a quite strong assumption because it implies several things, like these rings are Noetherian, regular local rings, they're stable by composition, for instance, stable by division. So it's quite useful. But we need to add more axiom for our purpose. So I gave some of the three following ones. So the first one is a kind of stability by blowing down. So if you take formal power series F and you assume that it's convergent after, it's a temperate, sorry, I would say temperate when you belong to this K algebra. So if F is temperate after blowing up, then it was temperate initially. Another property is that if F is not temperate here, it's formal but not temperate, and we consider its hyperplane section, then in general, its hyperplane section are also not temperate. So the set of hyperplane section for which it's temperate, it's small, it's at most countable. And I recall you that we assume that the base field K is uncountable. Okay, and maybe the most important axiom is what we call temperateness. So it's a bit technical. I wrote here this axiom, so it's not really important if you don't get it for the moment, or just for, you can see it at least once. So we denote by gamma of t some algebraic power series in one indeterminate t, that we assume of degree D over the ring of polynomials. And we consider other power series A1 up to AD of TZ, so in two variables. And we assume here that it's a power series in Z with coefficient in the ring of polynomials in T. So it's a bit tricky. It's not the same as being polynomial in T with coefficient in the ring of formal power series. Okay, it's more technical. Okay, we assume that the powers of gamma up to gamma to the power D minus 1 satisfies, if you take the coefficient, you multiply them by the AI, you obtain something which is temperate. So then this implies that the AI were themselves temperate. So it's a tricky axiom. For the moment, I don't want to talk more about this, okay? But for this kind of families, Weierstrass temperate families, we obtain the following result. So we have the analog of Gabriel's rank theorem. So this rank theorem that say if you consider a morphism of temperate power series, then if the two first rank are equal, then the formal rank is equal to the temperate rank. So here, the temperate rank of phi is by definition just the dimension of this quotient. Okay, so it's the analog of the analytic rank, but here we replace the ring of convergent power series by the ring of temperate power series. Okay. So I can give some examples of Weierstrass temperate families. So the first one is the ring of convergent power series over C. So not over R, because we need to work over an algebraically closed field, but if we have this rank theorem for the ring of convergent power series over C, then we obtain easily the same for the convergent power series over R. And what is new in this approach already for this example is that the proof of the rank theorem here is purely algebraic. It's purely algebraic, and the only analysis used to prove this result in the Gabriel case is concentrated in the fact that we need to prove for this ring of convergent power series that it's temperate. So to prove that this axiom is satisfied by the ring of convergent power series, we need to use analysis. And this is the only point where the analysis is involved. Okay? The rest of the proof of this result is purely algebraic. Another example of a family of Weierstrass temperate family. So it's the following that we call Eisenstein series. So it's a bit technical at first sight, but don't worry. So we consider a unique factorization domain called A, and we assume that it contains an uncountable characteristic zero field. We denote by L its fraction field, and K it's an algebraic closure of L. And then we consider this kind of algebra here. So we consider the power series that belongs in these rings. So what is AF of C? So AF, this is the localization of A with respect to F. So it means that this is the set of elements that can be written of the form G over some power of F, where G is in A and K is some integer. Okay. And we work over, we need to add some C being in K, so it's algebraic over A. Okay. It's a bit tricky to consider this kind of power series, but this form a ring, and we can prove that this family of ring is a Weierstrass temperate family. So you can forget about this definition here, but what you need to know is that this particular example of a Weierstrass family will be used to prove the first result of Pawłowski. So my goal is to explain how we use this rank theorem in this situation to prove this Pawłowski result. Okay. I'll come back to my initial question, and I need to introduce more terminology. So I will talk about Nash locus of a subanalytic set. So I consider X to be a subanalytic set of pure dimension. So I said that for a point P, X, the germ of X at P is Nash, if there exists another germ, Y, of an analytic set, at the same point, that contains X, and that has the same dimension of X at this point. So it means that X may not be analytic, but it's contained in an analytic set of the same dimension. Okay, so it's exactly not the case of the example of Osgood, where I come back to this previous example. It was there. Oops. In the example of Osgood, here, the image of phi of R2 was subanalytic, at least locally, and but its Zariski closure, the smallest analytic set contained in this phi of R2 was R3, which has dimension 3, while phi of R2 is of dimension 2 at 0. Okay, so this is typically not the case where the origin here, the origin is not a Nash point of this image of phi. Okay, so I come back to my definition. Sorry, where is it? It's here. So we can think about this. This is not completely correct, but we can think it's almost correct. So roughly speaking, a germ is Nash if it's the image of a regular map. So a map for which the theorem of Gabriel is satisfied. Okay. So this is a case of pure dimensional subanalytic set. And in general, if X is a subanalytic set, we say that it's Nash at the point P if every equidimensional part is Nash. So this notion has been introduced by Wilson, Millman, and Schwartz in the 80s. And we can define the set of Nash points, so n of X, as being the set of points at which X is Nash. And we need to consider all the points of the ambient space. So I come back to my first result that I presented before, which is in fact more general here. So we consider X to be a subanalytic set. Then both the set of points where X is not semi-analytic and the set of points where X is not Nash, both of them are subanalytic sets. And both of them are of dimension small compared to the dimension of X. Okay? So I will present the main ideas to prove this result using this rank theorem. So first, we need to, so I will present the strategy of this proof. So first, it's known for a while, we learned this by the work of Paruski, and it was already present in the work of Pearson and Milner, that we need to prove this result only for the set of Nash points. If you know the result for the set of Nash points, you can deduce quite easily the same result for the set of semi-analytic points. Okay, so that's the first assumption. We just need to prove the result for the Nash points. Okay, so the first reduction we can do is that we can assume that X is closed, because we can easily see that the set of Nash point of X is also the set of Nash point of its closure, the Euclidean closure. We can also assume that X is equidimensional, because if XD here denotes the D-dimensional part of X, then the Nash point of X is the intersection of the Nash points of each of its equidimensional parts. Okay, so we assume that X is closed and equidimensional. Therefore, we can use the uniform distinction theorem to obtain a map psi, analytic map from manifold M, real analytic manifold M to X, that is proper and generically immersive. And in this situation, we have exactly what I said before, that if we are the set of points of X which are not Nash, is exactly the image of the set of points of M at which psi is not regular. Reg of psi here is exactly the regular locus of psi. So psi is a map from M to X. And we can consider all the points of M at which psi induce a regular map. And we have this equality here. And therefore, Pawłowski's theorem is reduced to prove the following result of Pawłowski, that Pawłowski proved 2 years later than the previous one. But in our proof, we need to use this result to prove the first one. So this is the following. We consider psi a map, an analytic, real analytic map, or a complex. Here, we generalize, we change a bit the setting. We work or in the real or the complex case. So we take an analytic map from an open subset of Kp. Then the complements of the regular points of psi in omega is an analytic subset of omega and proper. I mean, it's not equal to the whole omega. Okay, therefore, we can use this result because this set is proper. It's imaged by psi, which is because this set omega minus the regular point of psi is analytic, and because psi is proper, its image is subanalytic. And therefore, X minus the set of Nash points of X is subanalytic. Okay. So I don't want to talk about the second part, of this result of Pawłowski about the dimension. I will not say anything about this, just it's not that difficult. It's a bit technical, too technical to be presented here, but it's not the difficult part of the proof of this result. So I'm just focusing on this result, that these sets are subanalytic. Okay, so we are reduced to prove this result, second results of Pawłowski. So what's the strategy of the proof? So we consider phi, this map defined in the following way. So I recall you. So here, I gave the proof of these second results in the complex case. So psi is just the map from omega, which is included in C, the P, to Cn. And I want to prove that the set of regular points of psi, okay, or is, let's say, Cp minus this, is analytic. Okay. So here, in fact, I will not prove that it's analytic. I will just prove that it's subanalytic. In fact, it's enough to prove our previous result. But once we have that proof that it's subanalytic, it's not very difficult to prove that it's analytic. Once again, it's a bit technical, and I don't want to enter in the details. So I just prove this. Okay. So first, I do this trick. I define phi, this new map, defined in the following way, that allows us to see psi as a family of analytic map germs parameterized by omega. So we distinguish two parameters, A and X. A is a global parameter living in omega, and X is an infinitesimal parameter in some sense. And for each A fixed in omega, we can denote by phi of A, sub A, the germ map between Cp and Cn. Okay, so this germ map, germ, induces a ring morphism between the rings of convergent power series here, like this. But we have more than that. In fact, we can do the following. So for each I, X of I is sent over some power series, okay, let's say phi I of U, but this depends analytically on A. Okay, so for each A, we have such a morphism here. So Xi is sent over something like this, but this can be expanded like a power series that I will denote by, let's say, phi I A U to the power beta, here A beta, where beta runs over N to the P. Like this. Okay, so I can say this as a power series in the indeterminate U, okay, with coefficient where, but this, in fact, they're leaving this coefficient in this ring O of omega, which is the ring of analytic function on omega. Okay. And instead of working over this ring of power series of omega, because I prefer to work over some field, I denote by L the fraction field of the ring O of omega, of analytic function on omega. And I consider this map, ring morphism, phi, let's say phi L hat, between the ring of formal power series over L to the ring of formal power series in U1 UP. So it's defined in the following way. Xi is sent over phi I of AU, okay, which is seen as a power series like this. Okay, so I put a hat here because I can define a phi L without hat in some temperate way, in the following way. So as I said before, we could consider this map like this. That sent Xi over this phi I of AU, but because I prefer to work over some field, I introduce this map phi L hat, but I can work over these rings also, and the union where F runs over all the non-zero element of O of omega. So this ring is almost temperate. It's not exactly temperate because the fraction field is not algebraic field. I do not want to enter into detail, but you can think about this family of rings to be a Weierstrass temperate family of rings. And I can define this morphism phi L from this ring to this ring in this way, previous way. Okay, and I will see that I can apply the rank theorem for this map. Okay, so I go on. I consider now a regular point of phi, and I denote by R the generic rank of phi at the point A. So in fact, it does not depend on A. It's the same at any point. And because it's a regular point, by definition, the three ranks are equal. So in particular, this rank is also equal to the analytic rank. Okay. So this means that the kernel of phi A star contains enough elements to have the right height, let's say. So if I denote V, it's the zero locus of this kernel. Okay, it has exactly dimension. The dimension of V is exactly, I don't want to say something wrong, it's exactly R. And therefore, after linear change of coordinates, I can imagine, so this lives in C to the N. C to the N, it's also C to the power R times C to the power N minus R. And I can consider the projection of the first R coordinates, pi. And after some linear change of coordinates, I can assume that this projection restricted to V is finite. So this means exactly that we can find Weierstrass polynomials, Pi, of this form. So they're Weierstrass polynomial with respect to this last variable, xr plus I. That belong to this kernel. Okay. So the coefficient of these polynomials here are power series in x1, xr, whose coefficients are analytic locally around A. Okay, so they're analytic in some open neighborhood U of A that is in omega. But U may be small compared to omega. Okay. Okay, and by what I call the extension lemma, if I have a bit of time, I would say a few words about this, but I don't want to talk about this. It's a bit technical for the moment. We can assume that, in fact, the coefficient of Pi, which are just analytic in some U, so let's say in this ring, are in fact can be extended in a meromorphic way over all omega. So this means that they live in the fraction field of the ring of analytic function of omega that is denoted by L. I will call you that's the fraction field of omega. So we can extend this coefficient as meromorphic function over omega. So in particular, if I come back to my bit strange algebraic morphism that I denoted before by phi L hat, these pi are in this kernel. And because they're Weierstrass polynomial with different, with respect to different indeterminates, the height of this ideal is bigger or equal to the number of such polynomials, so n minus r, and therefore the formal rank is less than r. But on the other way, this formal rank is greater or equal to the generic rank, which is itself equal to r, because this is the generic rank of phi a in any point a. So it has to be equal to r. Okay, so we have proved here that this generic rank is the formal rank. So we can apply the rank theorem to show that this temperate rank is also equal to r. Okay, so the kernel of phi L, like this, is also of height n minus r. So we can also prove that, as we did before, it contains Weierstrass polynomials like this kernel. So that's what is written here. The kernel of phi L contains Weierstrass polynomials that we could denote in the same way as before, but it's not important. That belongs here to some ring of this form, because I recall you that L here, phi L, is a ring morphism between these two rings. Okay, and this ring is a union of ring of this form here, Okay, so we can take f to be the same for each of these Weierstrass polynomials. I have a finite number of them, and so they all live in this ring. So this means that, so I make a picture here. I have my whole open set omega, and I have Weierstrass polynomials whose coefficients are in omega localized at f. So it means that I don't know what is f, some f equal to 0, it's some hypersurface in omega, and outside f of equal to 0, I can pick any point a or a prime. I should have written this in a different way, a prime, let's say. I can evaluate this coefficient who lives in this ring at a prime, and I obtain Weierstrass polynomials, which are, because they were in the kernel of phi L, they're also in the kernel of, let's say, phi star a prime for any a prime which belongs to omega, but not in f equal to 0. Sorry, omega, but not f equal to 0. Okay, I'm sorry. Like this. So this means what? This means, it means that the whole set omega minus f equal to 0 is contained in the set of regular points, because at each a prime outside f equal to 0, this kernel here contains this Weierstrass polynomial. So the height is at least n minus r. So it means, as I did before, that the analytic rank at these points is exactly r. So it's regular. So that's the idea. And we finish the proof by induction on the dimension of omega. I can consider this set, which is a dimension less than the dimension of omega. I can stratify it in a finite number of smooth analytic manifolds. And I can make an induction on each part, each piece of this stratification, where we prove what we did before, but for some families, for some, let's say, maps that I would denote by, let's say, psi. So from omega times Cp to Cn 0, but here omega is not necessarily open in Cp. Omega is open in some Ck for some other k. Okay, so it's a bit more general than what I did before, but in our work we call such a family an admissible family. Okay, this is roughly speaking the ideas of the proof of Pavlovsky result and how we use the rank theorem to prove this result. I think I have 3 minutes, something like this. So I will say a few words about the. I remember I talked about the extension lemma, saying that if the polynomial pi's, which are Weierstrass polynomials, have coefficients which are analytic on some small open set U, then I can extend them as meromorphic function on the whole omega. So this is the following results, extension lemma. So we consider the same situation as before. And I assume that I have one polynomial, so it's a bit simpler, just one Weierstrass polynomial P. And I replace xn by y here, such that P is a generator of the kernel. The AI are power series in X whose coefficients are analytic on some U, which is open and small. And this technical condition is just to say that they're Weierstrass polynomial at any point of U. Okay, I can expand this power series AI of AX as power series in X. And the coefficient here, so the AI beta belongs to the ring of analytic function in U, over U. And the extension lemma says that we can extend this function as analytic function on the whole, not on the whole omega as analytic function, sorry, but as meromorphic function. So the idea, very roughly, is that saying that P is in the kernel means that if you replace P, the X by its images, so X1, X, let's say by phi1 of U, phi n of U, you obtain 0. Means that it's in the kernel of phi. Okay, and saying that this is equal to 0, you can expand this as a power series in U. And saying that this power series is equal to 0 means that each monomial in this expansion is equal to 0. So writing down that these coefficients are equal to 0 gives you a system of linear equation in this AI beta. The only problem here is that this system of linear equation is infinite. We have infinitely many equations because we have infinitely many monomials in U with infinitely many indeterminates or unknowns, which are the AI beta. But because this polynomial is the generator of this kernel, this system has one only solution. So that's the trick. And then we need to use some lemma called the Chevalier lemma to prove that we can consider finite subsystem of this infinite system of equation. And using a trick, a very smart argument due to Pavlovsky, we can prove this extension result. So I will not enter into details. I think my time is over. So thank you very much for your attention.
Thank you, speaker.